All right, so this is the last of our Reach Ahead lessons for Unit 2. And this one deals with two types of organic compounds, amines and amides, and the reactions that form them. So an amine functional group is one with nitrogen in it. And you should be familiar with this if you've taken much biology at all from, for example, amino acids. But when a carbon chain has nitrogen in it, the IUPAC naming for that involves dropping the E from the primary chain on which the nitrogen is found, and we add amine at the end. And the nitrogen, just like carbon, will cap itself with hydrogen atoms. So it's going to bond to hydrogen anywhere it doesn't bond to the carbon chain. So the simplest example is, methanamine would be the simplest, but the simplest example in this lesson is ethanamine. So this tells us that it is ethane. So that's going to be a 2-carbon chain. But on the first carbon, which of course doesn't matter which direction you count, we will find a nitrogen, because that's the definition of an amine. And so if we draw here nitrogen, and then keep in mind that we said the nitrogen will cap itself with hydrogen. And know that nitrogen's carrying fastest 3. It typically makes 3 bonds, so it needs to make 2 bonds to hydrogen like that. And that would be ethanamine. The second example is propan-1-amine. Right? So propan tells us we have a 3-carbon chain, of course. And on this says we have an N on carbon 1. So we can have carbon, carbon, carbon. And I'm going to start my count from the bottom. It makes no difference. You can just easily start your count from the top and put the amine group there. So I'm going to put mine on the bottom. And so we'll say here we have a nitrogen and 2 hydrogens attached to it. All right, and then I want to draw at least one using a skeleton diagram. So here we have 2 butanamine. So butane, of course, is 4 carbons, 1, 2, 3, 4, just like that. And we're being told here that we have an amine group on the second carbon. And we would draw it like that. All right, so these is quite straightforward. I didn't put a section in it on the note, but you can also note that just like alcohols or any other functional group, you can classify these as primary or secondary. So this one here, of course, is primary. First one. The second here is a secondary, or is also primary, pardon me, because it's on a terminal carbon. But this one here would be a secondary amine, because it is on a carbon that's connected to other carbons. But one of the things that makes amines a little bit more troublesome, not troublesome, just one of the things that makes them interesting, is that nitrogen can make 2 more bonds. Nitrogen makes 3 bonds total. And so there will be cases where groups will form off of the amine group. So the nitrogen itself could have things other than hydrogen coming off of that. In that case, we name those things by using an N. So normally we would say like 3-bromo to tell us that the bromine is on carbon 3. Well, if we say N-bromo, then that indicates to us that the bromine would be found on the nitrogen. So here we have N-chloroethanamine. So we would draw ethanamine like this. All right, but then the nitrogen itself would be bound to a hydrogen and to a chlorine. Now, we're not going to draw that hydrogen because we don't draw hydrogen in, excuse me, in the stick models. But there we go. So this is N-chloroethanamine, where we have a 2-carbon chain, and we have a nitrogen, and the chlorine is coming off of the nitrogen, not off the carbon chain. In this example over here, N-ethylpentane-2-amine. Oh, that D is a typo. Ignore it. We again have a carbon chain. This time it's 5 carbons. Whoa. 1, 2, 3, 4, 5. I might go that a little bigger actually. 2, 3, 4, 5. Just like that. And in this case, we're being told that carbon 2, put that down a bit. I really didn't plan this well at all. There we go. Carbon 2 has an amine group on it. And then that amine group itself has an ethyl group coming off of it. So that means that off of here, we would have a 2-carbon chain. All right, so that is the ethyl group coming off of the amine. And this is the amine group itself. So that would be N-ethyl pentane 2-O. Now, in our last read-ahead lesson, we learned about cyclic alkanes and aromatics. So amines can also occur with cyclic alkanes and aromatics. Oh, this says N-benzyl. Of course, this should say N-phenyl. I'm not going to go back and change this video right now. If I remember, I'll go back and change the sheet. But if not, you can cross it out. So N-phenyl protein. Holy crap, what's going on here? Well, before we get too concerned, Coke tells us that we have a 3-carbon chain. 1, 2, 3, just like that. And that carbon 2 has a double bond. And that carbon 1 down to an amine. And then N-phenyl tells us that that amine is stuck to a benzene ring. And so there we go. And this would tell us that we have 1, 2, 3 carbons, so that makes it a Coke. 2 amine, because the double bond occurs on the second carbon. The amine occurs on the first carbon. And attached to the amine is a phenyl group, and so we call that an N-phenyl group. So there we go. In the second example, they ask us to draw in the second example, they ask us to draw a dimethyl cyclopentamine. Okay, well, cyclopent is easy. 1, 2, 3, 4, 5. We fill it in, so a little pentagon. And then, of course, it doesn't matter which carbon we take the N off of, because any carbon we do it will be number 1. And then both of these have methyl groups. And so we would just draw it like that. And note, I'm not drawing a circle or anything in here. This isn't benzene. This is like alkane. That's a 5-carbon ring with an amine group off of it. And then in this case, both of the methyl groups come off of the amine. And there we go. Now, from there, we wanted to look at a few reactions of amines. All right, and so the first example is that we can reduce a nitrile and nitrile is a very specific type of compound. So we could reduce a nitrile, which I'll explain to you what it is, using a hydrogen-rich compound, such as lithium aluminum hydride, to reduce the carbon-nitrogen triple bond. So a nitrile is something that has a triple bond to nitrogen. And so I'm going to use this example. CH3CN. This is a nitrile. Right, and we can react it with lithium aluminum hydride. And it's those 4 hydrogens that are specifically of note here, because these 4 hydrogens can react, they can break the 2 pi bonds, and what we can be left with is there, and then C, and then N, and now the 4 hydrogens will end up in this location like that. All right, so you can break the triple bonds. In breaking 2 pi bonds, that makes 4 more connections we have to make total, and all of them will be made with hydrogen. So this is an example of a practical way in the lab that we actually can produce an amine, is we can take a nitrile, a compound that already has a triple bond to nitrogen, and we can cause it to be broken and replace everything with hydrogen. Now, there's seemingly an easier way, which is the most straightforward way to make a primary amine, would be to take any haloalkane with ammonia. So we could take, say, CH3 and CH2. CH2Br, or we could take bromoethane. I gotta tell you, the form recognition on this device is a little bit designed at this point. So we can take this compound right here, and we can react that with methane. With ammonia, right, which is NH3. And in so doing, when we do this particular reaction, this bromine will react with one of the hydrogens, right? And what we end up with is essentially, I'd like to be clear, this is an oversimplification, as these things always are. But in the short version, we get an amine, so we get an NH2 sticking there, and then we also get HBr. Right? And again, it's a bit of an oversimplification, because what we actually tend to get is NH4Br, but for the sake of this lab, that would be an example. So that is a really simple way that we can produce a primary amine. Now we have an amine group on the end of that. But the reason that I showed you the first reaction and not this is, and again, I have no expectation that you'll memorize these. You won't be tested on these reactions, but I want to show them that the problem with a reaction like this is that it will keep going. So we can actually track what will happen if this reaction continues. Now, if we take this product, if we take our primary amine, it will now be in the same place as the original haloalkane started with, which, if you remember, had a bromine on its terminal carbon. And so this reaction will lead to a second reaction here, where one of these hydrogens and this bromine will react. We actually end up creating a new compound. So we will actually end up creating a secondary amine, where we have 2 carbons like this, and then the bound, the central nitrogen of the hydrogen coming off of it, and then it will now be stuck to the second chain. So it will have 2 carbons coming off of it. All right, so you can see that this reaction keeps going this way, And of course, that nitrogen still has one more hydrogen that it could potentially react. So we could then, of course, take that the product from that second one, and we could allow it to react a third time. And in fact, that's what will happen under normal conditions. If this is left again in the original container, is that you will get another third reaction happening. Where this hydrogen will react with the bromine on that again. And that will form for us a situation where you have two chains coming off of the nitrogen as well. So now we would have CH3, CH2, CH2, CH3, and CH2, CH3, with a central nitrogen. All right, and so that's just an example of how we can produce primary, secondary, or tertiary amines just by adding ammonia. But we need to be mindful that, like so many other situations, these reactions will keep happening. Right? Again and again and again in the presence of ammonia. So the reduction of the nitrile, the first example, is how we would produce a primary amine if we actually want to collect that amine and have it remain and not continue reacting. Again, I don't expect you to remember these. I'm just trying to introduce you to the idea, the kind of grand complexity of organic reactions. There's lots of different ways they can proceed. And that's what makes organic chemistry so interesting and so powerful. But it does also make it challenging to learn because you have to be mindful that so many different things can happen. Anyway, having discussed amines, I also want to discuss amides. That'll be the end of this unit for you. So amides are like carboxylic acids or esters. They occur when nitrogen is bound to a carbon that is also bound to an aldehyde, also has a double bond to oxygen. And because a carbon must make 3 bonds to form an amide, it's not necessarily to number the location of the amide because it has to be on carbon 1, just like the carboxylic acid. And we name them by dropping the E from the primary chain's name, and this time we add amide. So the example here is propanamide, and that would be a 3-carbon chain. Oh, well, it's doing this thing again. Sometimes it does this. I don't know why it does this, but it just doesn't always play nicely. Okay, there we go. Oh, what am I doing? All right, and we call it an amide because it's got a double bond to oxygen, and it's got a bond to nitrogen. Actually, I guess being consistent. Like that. All right, and that would be an amide. So again, we do not need to give it the number because the amide has to be on the terminal carbon. So we just always know. Here we have a pentamide. We could have 1, 2, 3, 4, 5. And again, we don't need to give it a number because we always know that the amide will be on the terminal carbon. We can just go like that. And in this case, we have a methyl group on carbon 2. So we'll draw that in. And there we have 2-methyl pentanamide. But just like amines, it's possible that the nitrogen atom of the amide can have other alkyl chains on it. And again, instead of giving them the number of the carbon, in this case, we would denote them with an N to say that particular side group is on the nitrogen chain. So here we have N-butyl propanamide. So you would do propanamide first by drawing a 3-carbon chain like that. A double bond to oxygen and a bond to nitrogen. And then we would say that in this case, that nitrogen is bound to a butyl group. So 1, 2, 3, 4, 5, just like that. All right, and that would be N-butyl propanamide, meaning that the butyl group is connected to the nitrogen, connected to the N, and the main amide is 3 carbons long, propene. Same idea. Take a moment and draw this and pause the video and see if we get it right. And we're back. The hexamide should be 1, 2, 3, 4, 5, 6. If we get to this carbon, go down to nitrogen, and put a double bond to oxygen. And the nitrogen should be connected to 2 chlorines. All right, so that's N-dichlorohexanamide. Say hexanamide, not hexamide. All right, and then the last example we'll give is just to remind you that we can mix these things up. It can also exist with cyclic alkanes, or it can exist with aromatics. So here we have a benzene. Specifically, we have a benzamide. In that case, we would take benzene. And remember, for any functional groups that are complex coming off of benzene, we have to put it to a carbon because the benzene itself can't make more than 1 bond from any of the carbons. That would be a benzamide. And we're told that it's N-propyl. So off of the nitrogen, we would have a 1, 2, 3 carbon chain. Maybe I'll do this by highlight it after. And then we're told that it is a 2N-dibromo. So carbon 2 has a bromine coming off of it, and the nitrogen has a bromine coming off of it. So here we have the 2N-dibromo, bromo and bromo. Here we have the N-propyl. That's the propyl group coming off of the nitrogen. And of course, the amide itself is this group here. And so that would be 2N-dibromo N-propyl benzamide. And again, it's possible to have this on any different type of cyclic alkane, any aromatic. This is just one example. All right, and again, in the case of reactions that I don't expect you to know by heart, but I just want to show that there are many, many, many very complicated different reactions that can lead to the formation of amides. So I'm going to just show you 2 of them. And I'm going to put a link at the bottom of this lesson, part of your assignment, part of your homework is for you to go take a look at. If you look up literature methods of synthesizing amides, you'll find that there's hundreds of different reactions. So I'm just going to show 2 examples. The first is called the Schmidt reaction. And in the Schmidt reaction, we take a ketone and we react it with ammonia to form an alkyl amide. And you can pick a ketone of your choice. I am going to pick this particular ketone. All right? And we would know that this is 1, 2, 3, 4 carbons. So this would be butane 2O. Right? And in this reaction, we react a ketone with ammonia, NH3. And I'm actually going to draw it because in this case, drawing itself will make a difference in understanding how it works. And this has to be done in this presence of a strong acid. All the literature I found mentioned sulfuric acid. If you find mention of any other acids, then I'm sure you could use a different acid. But it's always been done this way. And this causes actually a really interesting reaction where the reaction breaks the chain right in the middle here. And what will actually, and then connects to both sides. And so what ends up forming actually is a bond to nitrogen here. And then that nitrogen bonds up to the group that remained. Right? And nitrogen will still have to have 1 hydrogen, like that. and then the other two hydrogens are released, I think, as H plus ions. So I wasn't able to see that specifically confirmed. I wasn't sure where they go, but as far as I understand the reaction. And so if we look here, we have the left side of this original chain present here. We have the right side of this original chain, right? 2 carbons present here. And then the nitrogen and one of the hydrogens from here can be found in the middle. And these 2 hydrogens are released. They're not part of the bond. And so there we go. So this is a crazy reaction, but it actually makes an alkyl amide. So this is an amide with an alkane group coming off of it. But specifically, for this very one here, if you look, this is a 2-carbon chain here. So this would be phanamide. And then off of the N group, we have an ethyl group. So this would be N-ethyl phanamide. Oh, looks like I planned it. All right. That tells you that that's the FN part. Oh. It's an amide. And it's got the ethyl group coming off of the amide. So it's kind of color coding that name, where it comes from. So that is an example of the Schmidt reaction. Right? And a Schmidt reaction will make an ethyl amide. It will actually break the chain right in the middle where the ketone is and turn it into an amide with an ethyl group tie. Whereas we can get a totally different reaction in something called the Schotten-Daumann reaction. And in the Schotten-Daumann reaction, we start with a halogenated aldehyde. And so I'm going to use a very simple one. Ethanol. Right, just like that. And in this case, it's halogenated. So I'm going to look at an example where this is connected to chlorine, just like that. And we can react it with a primary amine, an amine. So something that has an NH2 on the end. And I'm going to take the simplest example, which is just phanamine. Right, so we're going to look at this reaction. Where we would have 1 chloro, and now reacting with methanamine. And you can probably predict how this one is going to work. In case you can't. This chlorine and this hydrogen will react. And in so doing, we'll get that ethanol. So the group there with the double bond to oxygen. But now it will bond to a nitrogen, which will be bound to 1 hydrogen. And then that will be bound itself to a carbon. And then here the H and the Cl are released together that way. So I should make the Cl green, and just sticking to my color code. And I should put it at the end and just move it after, otherwise it's going to look stupid. So there we go. All right, I'm going to carry in on naming everything. This would be an N-methyl, because now it's a methyl group coming off of the nitrogen, ethanamide. All right, and then hydrochloric acid. And this reaction has to happen in the presence of a strong base. In this case, all the literature I found suggested the use of sodium hydroxide. Again, it's not my expectation that you will know or memorize these reactions, but I'm trying to demonstrate to you just some of the incredible complexity that we get when we try to carry out some of these chemical reactions. So there's a lot going on. So I hope that was helpful. But now you know how to name amines and amines. You'll certainly come across them if you do some reading in organic chemistry. Thanks for listening.